Hello everyone, welcome to part 3 of the Intro to FreeCAD tutorial for 3D printing. In the last video we talked about some of the basics of creating sketches in the part design windows and then creating 3D objects from those 2D sketches. So in this video, now that we know how to create objects out of sketches, I want to talk about importing objects, such as this FreeCAD logo here used to create this sketch. And I want to talk about how to, first of all, import images and move them around, and subsequently how to create images of objects that you'd like to create in the program and how to scale them to size. And then finally how to import them and create sketches over them and create objects out of them. So you can kind of create your own objects from any objects you have, or create models that involve those specific objects. So let's go ahead and get started here for importing images. So the option to import images into the program is located underneath the Workbench Selection pull-down menu here, just like a part and part design. It's located right here underneath the little image icon. So you'll notice that there's only two options here, and the one for creating an image in the project is right here. So once you click that button, there's going to be the usual screen for importing things into the program or opening things. So search for the logo or the image that you would like to import. And you'll notice right here the list of file types that can be imported into the program, and there's quite a few of them. I usually use PNGs because they let you have transparent backgrounds, which is useful for some projects. So once you're ready, just press open here. And just like when creating a sketch, it'll ask you which face or which orientation you would like for your image, and you can reverse it here and create an initial offset right here, just like with sketches. So once the object's imported into FreeCAD, it'll show up over here in the combo view for the model list, and you can click it and you'll notice that the size of the image is predetermined by the number of pixels that it has. And I'll talk more later about sizing ratios and scaling ratios for getting accurate object sizes. So this image, for example, was 1,000 pixels by 280 pixels, and the program automatically converted that into millimeters. So you can change the size and skew the image and stretch the image however you'd like. But if you'd like to keep a even aspect ratio, you can just divide or multiply the numbers that you have by the same amount to get the same aspect ratio, basically. So once you have an image imported into the program, moving it around is exactly like moving a sketch around using the placement option underneath Edit here. And so it's just like a sketch. You can move it in any direction you'd like, up and down, and you can also rotate the sketch in any axes that you'd like. So now we've talked about the basics of importing an image into FreeCAD and moving it around. I want to talk a little bit about importing images that you've either created and scanned in yourself, or created on the computer, or downloaded from the internet, and scaling them to the right size and figuring out the right ratio to pixels to millimeters or inches, and also cleaning up the image so you have something easier to work with. For this example, I'm using something called a Picatinny rail, which is a rail that you mount usually optics on. I used it to create a finder scope mount for my telescope, and I think it'll serve as a good example. The program I'm going to be using to edit the images is called GIMP, and you can download it on the image for free. It stands for Graphics Interface Manipulation Program, I believe, but you can find it pretty easily on the internet and get it for free. So when you import an image into FreeCAD, it'll base the size of the image on the number of pixels in the image. For this image, for example, if I imported it right now, it would say it's 905 millimeters by 640 millimeters. Well, we know that's not right based on the size that we see here. So we need to find some ratio between the pixels and the physical size in millimeters so that when we import it into the program, it'll be the correct size. The other thing we're going to want to do with this image is isolate the front axial view here and the side view here. So we'll end up creating two different images to import into the program to create a three-dimensional object. And we'll want to be able to center the object in the image when we export it so that it's directly in the center of the three axes in the program when it's imported. I'm going to be going a little bit into detail about the size scaling and size ratios. So if you're not interested in this, you can go ahead and skip ahead to the next topic, but I think it's useful if you're editing your own images to import. So one of the first things you'll notice is that the scale for the front view and the side view is different. This is 19 millimeters here, and this is 10 millimeters here, so they're definitely not equal. So we'll start with the side view here. If we zoom in the program, we can use the selection tool to measure the size here in pixels to create a good ratio for importing the image into the program. Usually you'll want two different measurements in order to figure out the most accurate ratio possible. So I'm going to go ahead and measure the first distance here, which is 10 millimeters. And when you measure the distance between 2 points, you'll want to technically measure in between the center of each line here, but we can't do that because the pixel is 1 and you can't go less. But if you take 0.5 off of each side to center in the pixel, that ends up being 1 in total. So if we measure from end to end, it's 62, but if we center it on each pixel, we need to subtract 1, which ends up being 61. And you'll notice, so 10 over 61 is our first, and our second will be 20 over 22. And luckily for us, in this first example, both of these ratios are correct. So now we have an accurate ratio for the side view, which is 122 pixels for 20 millimeters, or basically for every 1 pixel, or for 1 millimeter, you have 6.1 pixels. This would work if we imported into the program. If we measure the size of the actual rail here and imported it into the program, the size of the rail would end up being 82 millimeters, but if you look here, it ends up being a little messy in terms of the digits. So what I like to do is find a multiple of the ratio that's a nice even number for the size of the image, so that when you import it, you're not playing around with any tiny little decimals and losing accuracy. So if we multiply this by the 61, we'll get 10. So if we multiply that by 10, we'll get 100 millimeters. So that tells us our size needs to be 610 pixels, which will end up being the size 100 millimeters. Usually you can use the reciprocal of whatever the ratio is and multiply it by 10, usually to get an even number that'll work out well. I'll show in this second example. It gets a little bit more tricky, and you'll kind of see what I mean for that. So now that we know what the size of the image needs to be for the side view here, we can go ahead and trace the image onto a new layer here. So I went ahead and created a trace of the object here, and as you notice, this cuts off here. So I went ahead and just made, once you have the first part of it and it's repeating, you can just copy and paste over it as long as you need it to be. So the reason I traced this onto a new layer is because when you import into the program and you have a white background like this, you can't really see what's going on behind it in terms of the opposite side of the axis, because the white will be blocking. But if you have a transparent view like this, you'll be able to see what's behind it and if there's anything interfering or anything else in the way. And I think it's easier to kind of work with a blank outline instead of a bunch of white in the background. So you don't have to do it this way, it's just what I find easiest. So now that we've finished sizing the side view to the length that we want it to be, we can go ahead and auto crop the layer in order to confine it to just the parts that are visible for the layer. So since there's nothing in the layer over here or over here, it auto crops it to what is actually present, what pixels actually have value. So we want the object or the image, the side view here, to be in the center of our image, and we also want it to be the right size here. So if we just exported the object like this, the sizing would be a little strange in FreeCAD. So this is what I was talking about earlier, using sizing ratios. So if we used the width multiplied by our ratio, which is 1/6.1, we would get a funky looking number here. But if we use 610, like I used before, we get a nice even number. So what we're going to do is size the image or the layer here to 610 pixels, so that when it's imported into FreeCAD, you can enter the size as a nice even number instead of having to go all the way down to the 4th decimal place. Also, sometimes if you end up using a weird fraction, like for instance this one, it probably continues on past 4 digits. So if you size it based on the size of just the object, you might lose some accuracy. But if you use a number that's kind of rounded, like this one is, using the reciprocal here, you'll end up with a nice even number, and that way you won't lose any accuracy when you import it into the program. It's kind of strange, but it works pretty well. Now for this layer, you could also use 305 and get a nice even number here. But unfortunately, the width of this image is over 305, so we have to go with 610. So we want to change the layer to 610 for both dimensions here. And then we want the object to be, or the image to be, in the center of the axes in FreeCAD when it's imported. So we can go ahead and just hit center, and it'll automatically center the image in the very center of the image, so that when it's imported into FreeCAD, it'll be in the center of all 3 axes. So that is the X and the Y will cut through the middle like this. Now if you want to have the bottom of the image be at the 0 point, all you have to do is divide the size of the object in pixels by 2. So in this case, this is 82. So we can divide that by 2, which is 41, and then subtract 41 from the Y value to get it at that 0 point where X and Y would be 0, instead of having it half and half at a positive point and negative point here. So that's just an example there. So once we get the size right for the image, we can go ahead and hit resize, and you'll notice it'll be kind of hanging out here depending on its position. So we can go to the layer and just copy the layer using Control C, and then go to File, Create from Clipboard to create a brand new image based on what we just copied, so we don't have to crop down our original image and lose the part of the front view that we need to work on next. Now that we have finished the side view, we can go ahead and go to Export and export this object. And I usually like to use PNGs, so we'll go ahead and use that. And when you export, if you're using PNG, you'll want to uncheck Save Background Color, and make sure to uncheck Save Color Values from Transparent Pixels. Otherwise, the background will show up as black instead of transparent, which is what we would like. So now that we're done with the side view, we can go ahead and get rid of that. And we can go back to our original image and take a look at the front view here. Now the front view here is a little bit more tricky because these numbers here don't perfectly coincide with each other when we divide the pixels or the millimeters by the pixels. When I divided all these different measurements millimeters to pixels, I came up with these different ratios here. So you can see one was 1091, and then two were 1092, and then another two were 1093. So it's only one 10,000th or 1/1000th difference, but I still want this to be as accurate as it can be when it's imported into the program. So what I ended up doing is finding the average of all the measurements by taking the size in millimeters here by its size in pixels here and adding them all together to get the most accurate possible average. Then what I did is I took this number and this number, which is the first one here, 65.2, and the bottom one is 597, and in order to get them nice and neat, I multiplied each one by 5, which is down here, and then I took the reciprocal or the denominator number and put it here and divided by 5. So basically I ended up with the same thing here, but the important thing is that you usually take the denominator and then divide it by a certain amount until you get an even number here. So now that we know in order for the image to be 65.2 by 65.2, it's going to need to be 597 by 597. So now that we know what the size of the image needs to be, I went ahead and made a tracing of the front view here. And as you can see, there's a size for the radius here. So in order to get that curve as accurate as possible, I used the radius measurement in order to figure out the size in pixels that it would need to be by using the reciprocal of our size ratio here. So to figure out what the diameter of the ellipse would need to, or the circle would need to be, I just multiplied the radius by 2 to get the diameter, and then multiplied that by the reciprocal of our ratio in order to get the size in pixels. So that way, when I went to go make the curve for the tracing layer here, all I had to do was enter in the size that we found here, which ends up being, I just rounded up to 28. So we can go to 28 for each one, and then we can click and drag it over to the point it needs to be at, go to Edit, Stroke Selection, and then choose the size, solid color, and hit Stroke. And it was already there before, but you'll notice it'll create a stroke around the circle, and it matches the sizing of the radius as accurately as possible. So I just wanted to point that out for tracing curves. If you want to trace, you don't really have to, but I find it useful. The other thing you can do to get rid of any color in the background here, like if I wanted to get rid of all the white, you can go to Layer and then or Color and go Color to Alpha, and then choose the background color, whatever it is. In this case, it would be white, and then press OK, and you'll notice it'll drain all of the white valued pixels away. So now that I have the front view traced and ready to go, we can go to the layer and auto crop the layer, and then we'll do what we did with the side view. We'll go to Layer, Layer Boundary Size, and we'll use the number we figured out before from our sizing ratio here as 597, which will end up being 65.2 in the program in FreeCAD when we import it in. So we'll enter 597 for both, and then we'll center it so it's centered in all the axes, and then we'll hit resize, and then we'll just go ahead and copy that layer to a new image, and then go ahead and hit export as the front view. And again, make sure you uncheck this save color from transparent pixels if you want a as well as the save background color if you want a transparent background. So now that we've finished editing the images to be imported into FreeCAD, we can go ahead and get them imported and start sketching over them here. So just like we did before, we go to the second one is create a planar image in 3D space. And we'll go ahead and start with the front view right here. Now since it's the front view, I'm going to want it in this dimension here, and I want it in the center of the axes. So I'm just going to have a 0 offset. Now if I wanted it to be back a little bit, I would just change it to the offset that I wanted, just like before. So we'll go ahead and press OK. Now this first image here, like we talked about before with the scaling ratios, the program recognizes the pixel count and converts it to millimeters, so that's why it's important to have the scaling ratio we talked about before. So last time we figured out it was 62.5 by 62.5. And as we can see, here's the front view right here, and we'll go ahead and do the same thing for the side view. And we want this to be on the side, of course. So our ratio for scaling this one was 100 millimeters by 100 millimeters. And as you can see, we came up with two independent scaling ratios, but they are perfectly aligned in terms of the top and the bottom. And there's another reason I like to center the object in the center of all three axes, is because when you first do the sketch, you can do half of the sketch and then flip it over to the other side 180, so you don't have to guesstimate where all the points are, and that way you'll have a perfectly symmetrical sketch. So I'll go ahead and start sketching these now, and I'll show you what I mean when I get there. So this is an example of why I like to have the image centered in all three of the axes, is because when you complete the first side of the front view, if it's a symmetrical object, you can copy this first half of the sketch and paste it and go into the placement option and flip it 180 degrees. And then that way you can just go back into your original sketch, and it shows you on the one we flipped over where all the points are located. So that way you don't have to guesstimate where each point is, and that way it'll end up very symmetrical. So now that we've finished sketching out the first face, we can go ahead and delete the copy of the first side we made here. And if you want to check the symmetricality of your sketch, you can go ahead and just hit copy and paste the sketch. And then if you change the placement, like we did before, by 180 degrees, you'll be able to see if there's any outlying points or lines. But in this case it's symmetrical, but if one part was off a little bit, you would see a different line here when you flip it. But in this case it ended up symmetrical, so we can just go ahead and cancel and delete the copy we made. Now we'll go ahead and move on to the side view here. Another option you can do for a repeating pattern image like this one is to end the sketch at the end point of the first segment of the pattern, and then what you can do is copy that and paste it, and from the original image we know again how many millimeters this needs to be moved by, and you can continue to do this until you get it into the center here. And then what you can do is flip it like this using the Euler angles here. And when you flip it, it'll automatically go to the other side of the axis here. And you can keep doing that for these the second one here as well that we did. So we'll just go ahead and keep flipping these. And then this way, the first half on this axis is symmetrical to this second half of the axis. So we'll just keep flipping here. So when you flip it over, since this one was moved -10 from this one, you want to move it the opposite direction but with the same magnitude. So in this case, this one was moved 10 from a negative 10 over from this original paste. So when this one is flipped over, it has to be moved the same amount but in the opposite direction. So we'll go ahead and flip this one as well and move that in the same amount. Now if we go ahead and get rid of the image, you'll notice that they all are present. What you can do is just make a pad out of each of these individual sections here instead of tracing the whole entire segment if you are opposed to that. So to continue, I'm just going to use all these pads I created. If you'd like to, you can, for your image, if it's not symmetrical or if you don't feel like it, you don't have to copy and paste and flip and stuff. It's just what I'm doing for the example here to show that you can save time by just doing the first part of a pattern. So now that the side view is completed, when we pad it, we can use symmetrical to plane in order to extend it in both directions. But we need to know how long the side view needs to be in this direction, and in order to get it to extend past to the edge of the front view here. So what you could do if you wanted to figure it out is go into the front view here and figure out where this point is. But you don't need to do that. You can just go ahead and go into the pad here, pad option, like we did before, and select symmetrical to plane, and then look at the front view and keep extending until it is longer than the front is, because we're going to end up doing an intersection and we want them to be intersecting each other and have some overlap just to make sure. Now that we've finished creating all the pads for the side view, we can just go ahead and fuse them all together using the fusion operation here. And once we do that, we can use the pad option on the front view sketch in order to create a pad for it so that it overlaps the side view pads. So let's go back into the part design window and choose pad, and we'll choose symmetric to plane like we did for the side view and increase its length until it is overlapping and extending past the side view, so that way when we do an intersection there's no parts missing. So let's go ahead and press OK. Go back to the part window here and choose to make an intersection out of these two objects. And there we go. There is our completed example from creating a three-dimensional object from an image using just two-dimensional template images. And this is very useful for creating objects that you scanned in or taken pictures of, and I'll have a couple more examples later of what you can do with other objects like that. So I know I've already talked a lot about prepping your images and sizing them for importing into FreeCAD, but I want to talk a little bit about how you can take a physical object and get a accurate photo of it so that you can create a stencil of it to be imported into FreeCAD to either make a copy of the physical object or make something that is related to or involves the use of that object. One of the first things I want to talk about is you can't use, it's difficult to use a normal camera or like a phone camera or normal camera lens to capture an orthographic image of an object, and I'm going to go ahead and use just a cube in FreeCAD for my example here. So this is how we want the object to appear, but unfortunately most camera lenses are not telecentric. That is, they have an aperture within the lens working itself instead of at infinity. So if you take a picture with a normal camera lens, it appears like it would to your eye with a kind of like perspective view. So the sides are distorted, or the dimensions will be distorted. But there's a couple different ways to get a more orthographic view of an object so that you can create a good stencil, an accurate stencil from it. And the first option for doing so is using a scanner. So in this example, I scanned the circuit board for a webcam I had to make a housing for it to adapt to my telescope. If the object that you're trying to get an image of is relatively flat, you can put it on the scanner and scan it to get a pretty accurate depiction of the image and its dimensions. One of the issues with using a scanner, if the object's not perfectly flat, is that it has a very shallow depth of field, as you can see, because this section of the circuit board was tilted slightly. So these are slightly out of focus. So it only is really practical for very flat objects, but it'll still give you a more telecentric view than the average lens. And you can use it to, you want to know the sizing of screws or the distance between screw measurements here, like for instance this circuit board, or its outer dimensions. So this is just an example of the initial scanned image and increasing the contrast and brightness, and then using this filter in GIMP called Edge Detect that shows you where the outer edges of each object would be located, so you can get an accurate reading on where the edges of the screw holes are or any other objects that are connected to it. And then from there you can make a tracing in a new layer of all the screw holes or the outer dimensions or whatever it is that you're interested in finding out. So the scaling ratio for an object like this works just like it did with the other one, only before you scan it or after you scan it, you measure its dimensions from either here to here or here to here, and then you just measure how many pixels are in that same space and find a ratio that way. So that's one useful way of being able to create an image of an object to work with. So another option for creating an accurate image to be imported into FreeCAD is, if the image is tiny relatively, or the object is tiny, you can use something called a micro lens. Micro lenses take usually a picture at a 1-to-1 ratio. So that is, whatever the camera lens images will be the exact same size as the sensor of the camera. So if you know the dimensions of your camera's sensor and its total pixels, not the active pixels, but the total pixels in that sensor, you can figure out what one pixel is equal to, and then use that measurement to figure out the spacing between objects in the image. So for this image, I was making a tiny lens mount for this webcam, and what I did was I ended up taking the dimensions of the sensor and dividing it by the total pixels in that dimension, and then the same thing for the side view, 15.7 millimeters, divided by the total number of pixels here, and then that way you can measure here in the image to a very, very accurate size. So for instance, this screw hole is about 140 by 140, so if we multiply that here, we can get a very, very accurate reading of what size this is, and that way we can also find a good ratio for scaling into the program. Micro lenses take a relatively accurate and telecentric picture of the image or the object that they're imaging, because they're so close to the object and the image in the lens is so far away that even though the depth of field is really shallow, like you can see here, this isn't very in focus here, it still gives a telecentric image and it's very accurate. So there's one more concept that I want to mention about mapping images in FreeCAD. I want to talk about how you can map or sketch images onto a curved object or an arc-like object. So in this example here, I made a logo for some of the lenses and optical stuff that I do, and what I did was I took the original picture, which was straight, just had all of the letters and characters straight, and divided each of them up into their own images, as you can see here. And then what I did was rotated the images a certain amount, and in order to figure out that amount, I divided 180 by the number of characters that I had, which was 5, which gave me a rotation for each image of 36 degrees. So if you have an image that you want to be mapped onto a curved surface, you can take the length of that object and subdivide it down until you get the complete number of parts you want, and the more there are, the higher resolution you'll have, but the more work you'll have to do. And what you do is you import each of those images into the sketch and rotate them either whatever angle you want to have them map onto the surface. So in this example it's 180. So you would divide 180 by how many images you have, and then import the images and rotate them around the center that amount, so that you can sketch in around the central point in order to create kind of a curved like image. Basically, it's kind of like integrating a rectangle over a curve in a way. You keep subdividing it and rotating all the little parts until they're around the circle of the object that you want to interact with, basically.